Good evening and welcome all to the today's session. Can anyone confirm? Is my screen visible?
Yes,
Yes,
sir,
sir.
visible.
Yes, sir.
Great,
Yes, sir.
great. Okay. So good evening and welcome all to the today's session, and I'll welcome everyone on behalf of Chem Club India team to attend this seminar. Before I'll start with the webinar or say seminar, I'll request all the participants to keep your microphone on mute. As and when we process, and if you have some doubt, you may interrupt me and ask your question, not an issue. Okay, but otherwise, request to keep your microphone on mute so that there will not be any disturbance and everybody will enjoy the session. So now let me begin with the discussion. In today's webinar, we are going to learn about how we can do the modeling in Aspen Plus for batch distillation unit. So our agenda is mainly going to be like we will first learn about the overview of batch distillation. What are the kinds of batch distillation? Mainly like batch stripper and rectifier. Then we are going to learn about design with geometry based modeling, means we are going to do modeling of batch distillation unit itself in Aspen Plus. And then we will have a little bit discussion on how you can build the integrated process. Okay. So let me start with first what is batch distillation. So before I will start, anybody wants to try the answer like what is batch distillation? Yes, Yogeshwaran, go ahead
Distillation
if
is
you
a
want to.
heated process where the two liquid mixtures are separated according to their relative volatilities.
Correct. That is okay. That part is clear. What is distillation is clear. I'm saying what is batch distillation? Like why we are learning this topic specifically? Like what is, because see, if distillation is clear, then what is the difference between continuous distillation and batch distillation? Why you need two different
The,
things?
basically the difference between continuous and the
Feeding
batch
going
distillation is
batch wise.
that in
Guys,
batch
one by one.
distillation we have to feed not continuously, and our product is taken out by timely, and then continue in continuous operation our feed is continuously going, and product also we taken continuously.
Yeah, correct. You're almost right. So let me explain things more in detail.
Sir, and we will be removing the desired purities in the fractions, sir. We
Yeah,
will
yeah, correct,
be
correct.
removing the desired components purity in the desired purity fractions. In the fractions, we will be removing.
Correct. So it will be in both. So let me explain things more in detail. When we say batch distillation, we basically refers to the use of distillation concept only, but it is in batch. The name itself suggests this is like a batch distillation. So that means concept is going to remain same. The normal distillation concept, same principle or say same phenomena is going to be applied here, but the thing is going to be applied in batch, meaning that the mixture is distilled to separate it into its component fraction before the distillation still is again charged with more mixture and the process is repeated. That means whatever things we are doing in continuous distillation means like my feed is charged, distillation is happening across the column or say tower. From the overhead we are getting the desired product, at bottom we are probably getting unwanted product, or I would say bottom is my desired one, then overhead would be the unwanted. So that same principle is applied here. The thing is that here we are charging the feed first into the tower or say first into the vessel. Once the feed is charged, after that the distillation process is happening, and it is happening until my desired product composition is achieved. And once that is achieved, I would say my batch is over, and then we are feeding my vessel or say unit with more mixture, and the same process is repeated. That means Here, the distillation phenomena is happening, but it is happening in a batch wise, like feed is charged, then distillation process is happening. As the distillation process is happening, it is trying to remove the unwanted purity from the desired product. And once we achieve the desired product target and my vessel content is, let's say, emptied out at certain time frame, we would say that my one batch is over. Now it's time to shut that system. When I say shut that system means stop the distillation activity and now feed the vessel again with the new content, or say same material but again new content, and then you process it again. That means here the feed charging and distillation is happening step by step, not like continuous column where the feedstock is added and distillate product is also withdrawn at the same time without any kind of interruption. Got it? In batch distillation, it is a stepwise, like
Yeah.
feed is charged, distillation is happening, and your product is obtained. While in continuous, we are charging the feed to the system, and at the same time, we are withdrawing the product as well. So your continuous is without any kind of interruption. While your batch system is having an interruption. When we say interruption, this is like a stepwise operation. Step 1 is charging the material into the system. Step 2 is performing distillation to achieve the desired product purity. Okay. Now, why people are using batch distillation in some of the operation and what kind of things we need to take care. So we need to remember that this is particularly useful when we want to complete certain number of batches within a fixed time frame. That means, let's say if my product is such a way that, and or I would say if my customer demand is that within 1 month they want some X quantity of the product. Okay. So in that case, if this is not feasible, I need to I need to consider the batch wise approach, that okay, how many batches I need to produce in order to fulfill their demand. Like let's say they are saying that I want 20 metric ton material, and now you need to calculate that how many batches we need to produce to fulfill that 20 metric ton target within the time span which they have requested. Let's say if they said that I want this material in 15 days, then we need to reverse calculate that okay, if this is my production rate, and if 20 metric ton is my requirement, I have 15 days time span. I need to check that how many batches I can complete in 15 days, and if that 15 days time frame is acceptable to fulfill 20 metric ton requirement or not. So this is going to be used when you have to complete certain number of batches in a fixed time frame. Okay. So any question on the basic concept of batch distillation, guys?
No, sir.
Okay, great. Now,
Hello,
mm, yes,
sir. Why should we go for a batch distillation rather than going for a continuous one?
yeah, I will tell you. I will tell you. See, there are couple of aspect. Okay. One thing is that in continuous distillation, what we usually do, we are starting the unit and then it is running almost on the same kind of product spec for a longer time. Correct? Your distillate product or maybe say bottom product spec is more or less remains same. When I say more or less, like I am saying that my bottom product purity I want probably 95%, sometime 96 or 97, but it is not like that. Today I want at 95, tomorrow I am saying that I don't want this bottom product, I want something else. It is not happening. Are you agree with me, Harry?
Yes, sir.
Okay. Now, when to use batch distillation is, let's say if I am having one unit, okay, which can produce different grade of material from the same setup. Okay. Or I would say that depends on market demand. I need to change frequently my product grade. So that time this batch distillation is going to help. Okay. And when we say this batch distillation, it doesn't mean that my whole plant is operating in batch. No, there may be a possibility that certain section is operating continuously and only this distillation portion is happening only in batch. Now clear, or you want further explanation?
Clear, sir. Thank you.
Okay, thanks. Now we are going to learn two main types of batch distillation portion. The first is called batch rectifier. That means we are interested in my overhead product spec. So if you see here on the screen on the diagram, we have a pot, okay, or we say reboiler, but pot along with reboiler, okay, I would say. Or if this is not a reboiler, let's say if it's a pot, then we are introducing steam for the heating purpose. So it depends on what kind of configuration your system demands. Okay. Sometimes somebody is saying that my reboiler is filled with XYZ material and we are using the distillation concept to have overhead material separation. Or maybe sometimes we have a pot. Most of the time people will say pot. If you see here, okay, this is my pot and this is the column, distillation column. Okay, this is our typical laboratory level apparatus. Okay, so this schematic represents batch rectifier where at the bottom we are offering the heating to the system. Through the column, separation is happening from the overhead. The material goes to condenser, material get condensed, come to the reflux drum, part goes to reflux, other goes to distillate. Now it depends. Sometimes you have only one receiver or maybe two receiver or three, depends. Okay, depends on how much quantity you are charging here and how much quantity from that you are going to get as a distillate product. So how this is going to work, that we are going to discuss. The simplest and most frequently used batch distillation configuration is batch rectifier, and it includes the pot or reboiler is filled with liquid mixture and heated. So that means we are saying that my feed is charged. So the feed is going to charge here into the pot or say reboiler. Okay, pot or reboiler. Now in this one, once the liquid mixture is charged and it is heated, the vapor flow is going towards upward in the rectifying column. That means as the steam is charged to the system, vapor is going to evaporate through the mixture and it will pass through the tower. Okay, let's say if this is a pack tower or maybe tray tower, depending on the internal, it passes through from reboiler or say pot all the way up to your column top. The overhead vapor is going to condenser. So initially the entire condensate is written to the column as reflux, improving the separation. That means when we are starting this system, okay, when the steam is going to be introduced initially, the column do not have any liquid coming back. So column do not have vapor liquid equilibrium in place. So what it does is initially only vapor is traveling from bottom to top. The vapor which get condensed is collected into the reflux drum, and initially for some time we are operating this as like a total reflux, the way we are doing in continuous column as well, so that we will have both liquid vapor equilibrium, or I would say liquid and vapor contact in the tower. Thus it will improve our separation. Okay, so once the reflux is started, your product or say your vapor liquid contact is better and you will have a better overhead product purity. So the first condensate is the head containing undesirable component, and the last condensate is the faint which also had favor. That means the initial condensate which you are getting, okay, that do not have the proper required product purity. Okay, because you don't have a reflux. But once the reflux is added to the tower, you will have a better separation within the tower, and the last condensate portion you will get it that also have the major desired product purity. Okay, and for batch distillation, or I would say any kind of distillation unit, the desired product is our heart. If we will get the desired product purity, then whatever we did is valid. Otherwise, it is no longer valid. It is not a worth. Whatever operating costs we have spent, whatever time we have spent, it is all like waste. Okay. So over a time, a portion of overhead condense is withdrawn continuously as a distillate while the rest is recycled as reflux. So what we are saying that once we get the desired product purity, okay, see, initially when you are running the first time, definitely you will going to take some sample, do the analysis, and once the product purity is matching, then only you will divert that material into your distillate receiver. But once you are used to that kind of things, you know that for a given feed, if we had it over a temperature so and so, my product is going to be on spec. So based on your practical experience, till that time you will operate column on total reflux, and then once you are able to achieve your desired product condition, you will convert your total condensate material into half or maybe some amount goes to distillate and remaining amount goes to reflux. So depending on reflux requirement, the thing is going to be there. Now, as the distillation progress, the relative fraction of heavy component increases. That means more like as the distillation is happening, that means more vapor and liquid contact is happening within the tower. We are trying to recover maximum lighter component based on the vapor liquid engagement in the tower, and whatever residual liquid will come back to the reboiler or say pot, that is nothing but only heavier component. So depending on the boiling point of your fluid and the steam temperature, the material is going to vaporize, and accordingly you will get the reflux and the separation is going to be there. And this type of system is going to be used for producing seasonal or low capacity high purity chemicals. So typically for specialty chemical unit, where as I mentioned that depending on market condition, the product grade is going to be changed. That means I'm saying that seasonal. Okay, let's say probably if the owner knows that between January to let's say April, they need certain kind of chemicals to be produced as their demand is more in the market. Let's say during June to or maybe May to September, if we are talking about let's say pesticide industry, okay, there they know that during monsoon season definitely the pesticide demand is going to be increased, so definitely they are going to produce their batches like probably April to July or August or maybe May to September likewise. So this kind of system are going to be used when my intention is to produce seasonal product or low capacity. Here the capacity is not as high as like what we saw or so what we typically see in the continuous distillation. But the advantage of this is since this has a low capacity, you will have a very high product purity. So in specialty chemicals, typically the requirement is to have 99.9 kind of purity, correct? 99.99% or 99.95 percentage. So that is the reason people are preferring this kind of operation. So any question on the batch rectifier, guys, before I'll move further? Yes, we will go ahead.
Yes, sir, sir. Sir, one more time explain the purity. How to how to use the reflex improve the purity of the distillation.
Your question is not clear. Your voice is not clear to me. Can you repeat it? What you are saying? I think you're talking about reflux, correct?
Yes, sir.
Yeah. So ask your
Sir, one
question
more
again.
time. Sir, if you give the reflex, how to the purity will be increased? One more time, just clearly explain.
So you are saying that how this reflux is going to increase the purity?
Yes, correct, sir. Exactly.
See, the reflux is nothing but what? The overhead vapor, whatever you are getting, is getting condensed. Okay. And same liquid we are feeding. So earlier, at the beginning of this operation, it only has vapor. So based on the steam temperature, the material is being vaporized. Okay, material is being vaporized. Now if I want certain component only in my distillate, it doesn't understand, like system doesn't understand, this pot doesn't understand that it has to only pass those lighter component only. Okay, based on the steam temperature, if the middle component, I would say lighter component, middle component and heavy component, let's say. So if middle component boiling point is lower than the steam temperature, then definitely it will also evaporate along with your lighter component. So this vapor which will travel from bottom to top, it also has those slightly heavy component or say middle component. So that's why when it get condensed, we are pushing back as that liquid as a reflux. So what will happen when the material is travel from bottom to top, the temperature here is more, correct? At bottom you will have maximum temperature, as you go up temperature will be down, and here we are also feeding the reflux. So the temperature here is, let's say, 80 degrees C, but the reflux which we are feeding is of 35 degrees C. So what it does, it will add that liquid on this tray, let's say tray number 1, and vapor which is there, it has to travel through that liquid. So definitely the vapor is also getting an engagement with liquid, and because of this cold temperature, it will also try to cool down some content. So whichever material is getting condensed through that vapor will come back here down. So the lighter material is easily going to evaporate again. So that's why it will not come back, and the heavier material will come back. This is how reflux is going to increase the product purity. Clear, Vivek?
Clear, sir. Focus.
Yeah.
Thank you.
Until when
Sir?
do we operate the column on total reflux?
Sorry. Until when we are going to operate the column on total reflex? That is your question, correct?
Yes.
Yeah. So now here the thing is that initially when the vapor comes and material get condensed, you will have zero liquid, correct? As the liquid is coming, you will get some amount of liquid level. Now, though here on screen we have not shown pump, but most of the time you will have pump, correct? So material comes into the pump and then pump is pumping. If let's say there is no pump, then what you will do, you will ensure that a sufficient liquid level would be there, and then you will start charging the reflux. Now let's say if you have started reflux, and definitely the level is going to deplete, but at the same time vapor is coming and it is maintaining, it is trying to maintain the level. So until, let's say, until your level remains same, until your level remains same, or say deplete, you will play with the reflux. But once the level start increase, that means now more amount of lighter content coming here into the section, and because of that you are getting. So once you have a sufficient liquid level, or say liquid level is now increasing, it is a time for us to divert the material into distillate. Let's say if you are operating first time, try to take the sample from the sample point upfront before you divert the material. Once you get the result, you try to transfer the material into the receiver. But as I was mentioning, once you are used to this kind of batches, you will know that once the overhead sections contain certain temperature, product become on spec. So at the same time, your liquid level is also going to increase. So you can route the material, excess material into the distillate. Clear now? Who asked this question?
Yes, sir. Yes.
Okay, okay.
Sir,
I think
sir,
Parikshit has
why
question.
we use, sir?
Yes, sir.
Yeah,
I wanted to ask
guys,
that.
one by one, guys, one by one.
Okay, so can I?
Yeah, go ahead.
Yeah, so sir, as you said, that batch distillation is used for producing different purity products. So doesn't the calculation change for the same? Like if you want to produce 95% product, so that requires different number of trays and different number of
See,
different diameter for the
I
column.
understood. I
So does
understood. Understood. See,
okay?
See, if I know that my requirement is to operate the column from, let's say, 90% product purity to 98. So during the design phase, the engineering team is going to consider the worst scenario of 98 percentage product purity, and accordingly they will do the design. Let's say later on, if the customer, one of your customer is saying that I am okay with 95% product purity, then if you share them a product with 98% product purity, you will not get additional premium amount for that 3% product purity, correct? Because they will say my requirement is not 95. If you give me 95 or 98, I don't have any issue. So for that, what we need to do, I will not say that, yes, definitely for 95% product purity, you will have probably low number of tray requirement, probably one or two tray requirement would be less, but this is not a small thing that I can stop my batch, open the tower, remove one or two batch, and I will operate it, correct? So during that time, when the product purity is low at customer end as a demand, that time we will adjust our parameter by reducing the reflux rate, and accordingly I will get a low product purity.
Okay, sir. Got my answer. Is it like we take maximum product purity for the design part, and then we
Guys, please at least don't mute myself. Okay, I think somebody is trying to mute.
Hi sir, as the bottom as a pot saturated with heavier components, the how will reflux flow will change? Like it will increase or you have to decrease at the end of the distillation process.
See, our intention is to meet our product target, correct? So your product purity is going to be affected, guys, one by one. Your product purity is going to be affected by top temperature. So if your top temperature is, let's say, increasing, you have to increase the reflux to maintain the temperature. This is one aspect. Second, if it is decreasing, you can reduce the reflux, or else you have another handle available at a reboiler end that you can play with your steam flow rate. Or third option is like if you have a bottom temperature control itself, which is linked with your steam flow rate. So based on your bottom temperature set point only, okay, your steam flow rate is going to vary. So these are the handle available through which you can control your overhead top temperature so that your product purity is going to be maintained.
Okay, sir.
Sir,
Yeah.
why we call this as a batch rectifier rather than batch distillation? I can get that
Yeah,
clearly.
I will tell you here. If you see, you all guys are asking everything like this is the only slide we have to discuss. Just try to wait. Once I'll go into the subsequent slide, you will get a better clarity. If you see here, our intention is to remove the product from the top section. So if you know that in column, top sections we are calling as rectifier, and bottom sections we are calling as stripper, correct? Sorry, my bad, my
Yes,
bad.
yes, yes, yes.
Okay, so if you see this batch stripping, okay, where we are charging the material into the top and product is collected from the bottom, while here we are charging the material into bottom and we are collecting our product as top. So here we are collecting the distillate, that's why we are calling this as rectifier, and here we are collecting the heavier product and we are charging it at top, and that's why we are calling this a stripper. So these are the two difference. Top section is my rectifier, bottom section is stripper. So if I am collecting product through the overhead portion of my unit, I would say this is a batch rectifier, and if I am collecting the product which is of my interest at bottom, then I would treat it as batch stripper. It was my bad that I haven't explained the things, and that is why you are getting so many questions. But our next topic was same, like batch stripper. So this is another configuration. Let me explain, and if anybody still has any doubt, we can discuss. Not an issue. So this batch stripper is another set of simple distillation configuration only. Uh, Here also it has more or less similar kind of parts, I would say, because if we see here, here we have reboiler column, condenser, reflux drum, and vessels to collect the material. Here also we have reboiler column, condenser, reflux drum or say pot, and you have a receiver which is collecting the product. Okay, so same phenomena, only is the location of my feed charging point and the product collection point is going to be different. If you see here we have listed that in this case, the charge port is located above the column, while here in the rectifier, the charge port is located below the column. Okay. And operation wise, same like high boiling constitute are primarily separated from the charge mixture. The liquid in the pot becomes depleted in high boiling component and enriched in low boiling one. That means the material is charging here, liquid comes back, it is filling the loop. Okay, and then when you are supplying heat, it is trying to remove the lighter component into it. Okay, so the lighter component comes here, again it will come here. Okay, again the vapor is there. So what we are saying that here in this section, the column sump is trying to enrich with the heavier component, while the column overhead, the pot, is trying to enrich with the light boiling component. Okay, and whatever amount is coming here as a reflux, it will retain here based on the boiling point of the individual component, and whatever amount will retain here as a lighter component, that is my non-wanted product, or I would say unwanted product for this stripper operation, and the main product is the heavier component are taken from this sump to the product receiver. Now clear guys, any question with respect to batch stripper and rectifier?
No, sir.
Okay, and I am still seeing 3 raised hand. So guys, if you don't have question, please lower your hand so that at least I'll be able to understand that how many participants have real question. SRS, Nitin, Sangeetha. If you have a question, go ahead and ask. But if not, then please lower your hand.
Sir, I have one question.
Yeah, go ahead.
Yeah, which one is more important? This is reflux ratio or the temperature of vapor leaving from the top of the distillation well? Which one is more controlling parameter?
Yeah, I will explain. Now, temperature of vapor leaving the column, correct? So you are talking about this. Don't think about stripper or rectifier. Now, ultimately both are linked. Let's say if my top temperature is 80 degrees C, okay, and we are condensing the material from 80 to let's say 35 degrees C. See, this 35 degrees C materials come here and it is trying to add cold duty to the column, correct? Ultimately what it does, the 35-degree material is going to exchange heat with the incoming material which is at 80 degrees C. Okay, so both are in hand. There is no thumb rule that only my top product temperature is governing. No, let's say somebody is saying that I am getting a product purity at 80 degrees C here at top and 35 here at outlet. Someone will say that I am having another combination where here I am having a 79 degrees C. Okay, but here even at 35 I am getting product purity, but that in that case he may probably playing with your reflux flow rate. Okay, so it is not that only the top temperature. Yes, top temperature is, I would say, more preferred over reflux. Like when I say I have two parameter which I have to maintain, so I would say that always try to maintain the top temperature first. The reason is if the top temperature is going to increase, it will also carry amount of heavy content in it, and then it is going to condense and you have to put it back. So yes, in terms of preference and priority, your top temperature is a must, but it is not that only this is the one which is doing my all activity in the distillation column. No, along with that your reflux is also important. Now clear, Mansoor?
Yes, clear. Thank you, sir.
Yeah, thanks. So let's begin further. Let's proceed further. Now there are couple of ways. Okay, So certainly we can say that in batch distillation, there are several operating mode which will dictate how the process is carried out. And we will explore them. The first is constant reflux and variable product composition. So in this mode, okay, my reflux ratio remains constant throughout the process. However, the composition of the product can vary. So what I'm trying to say that if, okay, if my distillate composition is different, okay, in different batches, then you may end up seeing a scenario that you are having the same reflux flow rate, but you will have a different product composition. That means what we are saying that reflux is remains same, distillate composition is varying, and this is going to be used when the goal is to obtain a specific product composition. That means you are playing with your bottom temperature. You are increasing the bottom temperature, and because of that you are getting high overhead temperature, or maybe you are reducing the temperature, you are getting a low overhead temperature, but my reflux ratio is fixed. So my column overhead temperature is not maintained constant, and because of that my product composition is going to vary. So somebody has asked a question that if I have a different composition, why we need to have one design, correct? Like we need to reduce the tray and something like that. So another handle that one would say that if my product purity requirement is low, I will keep same reflux ratio, okay, and I will increase the temperature further. My overhead temperature is going to be more, and thus I will have little amount of heavier carried over into it, and I will get lower product purity, and probably your batch time will be reduced. Okay, so there are couple of handles in distillation column. There is no thumb rule that if you do X, you will get Y. No, for each activity you have different handle, and depending on which handle you are playing, accordingly the things is going to be different. Okay, the second, this is the first, you can keep the constant reflux and you can play with the variation in the product composition. Second is variable.
Sir,
Yes, sir.
I guess you mute, sir.
No, your voice is not audible, sir.
I don't know how I am getting muted. Automatically this mute is happening, or I don't know, somebody in the participants is by mistakenly doing it. Okay, no problem. Whenever you are facing, or maybe let me keep this on my in front of me, so at least I'll be able to understand. So the second thing is variable reflux and constant product composition. That means my reflux ratio is going to be changed during the operation, and I am doing this variation or say manipulation in my reflux ratio in order to ensure that my product compositions remains intact throughout the process, or say throughout all the batches which I am producing. So that means if my feed to the charging vessel or say pot is having a different grade, or I would say, I would not use grade word, but I would say that there is a variation in your feed quality itself. Okay, you are not getting always a fixed grade or say fixed quality of feed to the vessel, but you are having a variation is not that much, slight variation.
So you are muted.
Sir, I think you muted.
Okay, I don't know why this is happening, but okay. So what I was trying to say that when my feed is,
Sir, repeatedly, I guess you muted, sir.
yeah, but I don't know how this is happening. Okay, what I was trying to say that why this is happening is If my feed composition is having a moderate variation and it is not in my control, okay, I am importing feed from someone, and because of that there is a variation happening, but I have to produce a batch with a particular grade product purity. So it is important for me to maintain the product purity. So I have the handle available with me is that I can play with the reflux ratio, so that at any point of time, if there is a variation in my feed quality, my product is still remains intact. Okay. Now the third type is optimal reflux and optimal product composition. So in this mode, basically, we are playing with both reflux ratio and product composition. So that means here we are saying that we want to achieve best possible separation. And we are also talking about our optimum operating cost. We are saying that we also want to optimize the energy consumption and product purity. That means, let's say if I am producing a product purity as 95 percentage, I am spending, let's say, 1 million capital cost on a yearly basis. Okay, this is just one example I am giving. Versus if I am producing, let's say, 96% product purity, I am going to spend 1.5 million operating cost on a yearly basis. So now one would say that for gaining just 1% product purity, we are spending 50% more operating cost on a yearly basis. Does this really worth? So somebody has to check that if I'll sell 95% product purity in market, I am getting X as a price. And now if I'll sell, let's say 96% product purity in the market, I'll get the Y as a price, and check the difference of X minus Y. See what delta you are gaining when you are selling the product with 96% product purity, and multiply with how much quantity you are selling on a yearly basis, and check that are you really gaining more than 500,000 as the revenue through that 1% better product purity? If yes, then it is worth to operate the system with 96% product purity, even though you are adding more than 50% operating cost compared to 95% product purity. But let's say if I am getting only uh, 3 lakhs, okay, as the revenue by selling the 1% better product purity throughout the year, versus I'm spending 5 lakhs, half a million means 5 lakhs as the operating cost, basically I'm losing 2 lakhs, correct? Or say I'm losing 0.2 million. So one has to do a trade off that at which point I am getting a best possible separation efficiency with the optimum operating cost. And if this kind of things are there, then we need to play with both reflux ratio and product composition depending on your feed composition variation. So these are the three different types of handle or say options available when you operate the column in batch distillation. Anybody has any question? Yes, Sanjay, go ahead. Sorry, Sanjay is waiting in the lobby. Okay. Okay, let me go further then. So now we are going to quickly go through the different applications of batch distillation available in the industry. So mainly this is going to be used in high purity chemical production, where we want to separate small quantity of fine chemicals. And this will ensure that high purity of the desired product is attained. And when we are talking about very high precision, okay, or say my product purity is very much critical, the batch distillation is allows the meticulous control over the separation process. It is not like you will not get that kind of control in the continuous distillation, because in continuous distillation you are continuously feeding the feed to the system and you are withdrawing. So if there is a variation in the feed quality, okay, if there is a variation in the feed quality, you will be affected by means of your product composition. So when I'm saying that my product purity and it requires high precision, okay, it requires high precision, it is mandatory that you should follow batch distillation, because in batch distillation, once we are charging the feed, after that only we are starting the distillation process, and when the distillation process is happening, we are not charging the feed again into it. So that means you have a better control for the separation, while in case of continuous distillation you don't have that kind of control. Second is solvent recovery process. So mainly the chemical processes, especially those involves high value added product. Batch distillation is ideal for recovering solvent. So those who has worked into the solvent recovery units or the solvent industry, they knows how much crucial this batch distillation is. And by carefully distilling and separating this solvent from the product, industry can minimize the waste and reuse this valuable resource, because this solvent is going to be reused in the process again. If you will not recover, then you are going to add that solvent again, and you are going to incur more operating cost to the facility. Rather than using batch distillation as an unit operation, try to recover the solvent, again reuse the same solvent in the process. You will recover your chemical, or I would say you will reduce your chemical consumption. And third and most important thing is pharmaceutical and specialty chemical industry, where the batch distillation is playing a significant role, mainly in pharmaceutical, because there the requirement is too stringent. Like I am talking about many medicines, correct, where you have high precisions. Okay, high precision is required. Yes, go ahead. Somebody is trying to say something. Anybody wants to?
Precision in terms of quality or tower means vapor liquid equilibrium, yeah, tower height, column diameter means precision in terms of what?
Yeah, I'll explain. See, tower diameter and height is dictated by your product purity. So once your design is done, tower diameter and product is fixed. Okay. Now the precision is with respect to your product purity. Let's say in refinery, one should say that I am okay with 99% product purity. But in pharmaceutical industry, where we are saying that medicines are prepared, so there it's not the case that 99% product purity is acceptable. If it demands that I need 99.99% product purity, that means it requires, even though it is 99.97, the batch is failed. So that kind of precision is required in pharmaceutical and specialty chemical industry, and that is the reason batch distillation is there. Because if batch, instead of batch distillation, I am using continuous distillation, and there is a variation in feed, slight variation in feed is definitely going to impact my product purity from 99.99 to 99.97, correct? And I'm not going to have that kind of flexibility, or I would say that kind of highly instrumentation which can measure this much variation. While in case of batch distillation, what will happen, since your feed is fixed, you have charged the pot and now you have started the distillation, you understood that if the temperature is this, you will get definitely this product purity, because your feed rate, sorry, feed to the tower is fixed. Now there is no variation in the feed itself.
Got it, sir.
Okay.
Got it. Thank you.
Yeah. So the precision which we are talking is mainly related to the product purity, not only in the batch distillation, but anywhere where when somebody is saying that I need high precision, so that precision means in operating unit it refers to the product purity. Yes, if you are in the design stage, engineering stage, and somebody saying that we are thinking of high precision, then the terminology is related to the dimension. But once the design is over, dimension is fixed, like this is the diameter, this is the height, tower is installed, or say unit operation is installed. Now I don't have the handle to change the physical appearance of the equipment, correct? The mechanical condition and the physical condition is fixed, geometry is fixed. Now only the option available with me is the operating parameter through which I can play to fulfill my desired product purity requirement. That's it. So any question guys on this application part? Okay. Now we are going to learn couple of fundamentals of batch modeling in Aspen Plus, because today we are going to cover one example of batch distillation model itself in Aspen Plus. Like I'm going to show you the live demo of how you can do the batch distillation modeling in Aspen Plus. Okay, so we will quickly go through the initial theoretical part and then we will start the exercise. So the batch operation or process has dynamic nature, meaning parameters such as temperature, pressure, flow, concentration, hold up is going to change over time during an operation. That means as my distillation is progressing, the hold up in the pot or say charge vessel is going to change. As the time progress, it will deplete. And we will see this when we will do the model, and when we will run the model, you will be able to see that, okay, feed has charged, now slowly it is depleting. Okay, that kind of live things also can be seen in model. Okay. This is the opposite of steady state or say continuous process, because in continuous distillation, your liquid level in the column remains same. Correct? We have a bottom liquid level control wall, which is trying to maintain a fixed level in the sump. Versus here, the pot or say sump where we are charging the feed, the liquid level is going to deplete as the distillation progress. The creation of model for such operation also implies the identification of initial state, a final state, and the sequence of state steps connecting to different recipes. If we are talking, that means when you want to run this kind of model, you have to identify the initial state, means initially what is the condition of your vessel. Okay, or say your charge vessel, whether it is filled or whether it is empty, that kind of condition we need to fix. Then you need to provide the final state and the sequential steps. Means if let's say my initial condition is empty, I would say that my next step is charge the material to the vessel, let's say for 10 minutes or maybe for 1 hour. And after that, I will say that next step is perform distillation until I will get desired product purity as XYZ. So that kind of sequential steps we need to model in the batch distillation unit in the Aspen Plus. Now, once you do this kind of modeling, the mathematical model for a batch operation or series of connected batch operation into batch process, which includes differential equations, characterize the time dependent behavior of process parameter. That means in the back end of Aspen Plus database, they have various mathematical models for the batch distillation unit. So once you run the model, it will try to fetch those differential equations which have a time dependent characteristics to calculate the whole batch process. Okay. And the third fundamental things which we need to learn is Aspen Plus capability with respect to batch modeling have been significantly improved over an year or say over the version they have upgraded. Okay, this batch distillation concept was not there in the earlier version of Aspen Plus. From version 10 onwards, this batch distillation is introduced. Version 10, 11, 12, 14, like now we have version 14 available in the market. So prior to version 10, this batch distillation was not available in the Aspen Plus software. So if somebody is using, let's say, Aspen Plus version 8, he or she may not be able to do the modeling of batch model in Aspen Plus. Okay, batch distillation is there, but see again, as we will go further, I'll explain things more in better. There are two different flow sheet. One is continuous based and another is batch. So I am referring to the batch model flow sheet. Okay. So once when we say that the capability has significantly improved, that means we can model the integrated batch, semi batch, continuous process along with the batch process in a single environment. Okay. So that means I'm talking about this system. If you see, this is my continuous operation. Feed is coming, heating up, and then here I'm charging. Is it happening with all guys? Okay, what about others?
No, sir, audible you are.
Okay, then those who have problem, it looks like there is some internet bandwidth issue at your end. So here if you see, okay, this is a constant or say continuous operation, and this is my vessel or say system which is operating in batch. So batch unit operation and flow sheet are solved dynamically inside Aspen Plus, even when it is integrated within a parent flow sheet contains steady state operation as well. That means normally we have to have an option to install sub flow sheet, and this sub flow sheet where I am modeling, let's say my batch system, and in my parent sheet I am modeling the hello, hello, guys, others, are you able to hear me clearly?
Yes, yes, clearly.
Yeah, yeah, thanks,
Yes,
Kedar.
sir. Yes, sir.
Yeah, yes, Raju, you want to ask something? Okay, no problem. So what I was saying that typically either if it is Aspen Plus or say Aspen HYSYS, we have a main parent flow sheet and we have one option of sub flow sheet development. So when we have a unit which comprises of some part as a continuous system and other part as batch, it is better that you should model continuous part in parent sheet, let's say, and uh, batch part in the sub flow sheet, and then you can interlink. Okay. Now the thing is that, okay, one thing one need to understand. Somebody will say that I will quickly move into this slide. Okay, so if you see here, this is the snap from Aspen Plus itself, that this continuous represent continuous simulation modeling, and the batch represents batch simulation modeling. So one should say that if I have to model batch distillation, I'll use this and not continuous. This is a typical question arise in everybody's mind. But for your knowledge, batch model flow sheet do not have batch distillation in it. So if you want to model batch distillation column, we need to refer continuous model flow sheet. And that is the reason we have listed here that since Aspen Plus do not have a module to model a batch distillation column in batch flow sheet, we are going to model batch distillation column in continuous steady state flow sheet only in our exercise. Or even you have to do, you have to follow that only, because you don't able to see that scenario at all. I will show you later on. Okay, so this kind of system we can do model in Aspen Plus. Now try to understand the difference between continuous and batch. Okay, this is mainly the flow sheet part. Okay, I'm not saying the continuous batch distillation or say, sorry, continuous distillation versus batch distillation, that we have discussed. Now we are trying to highlight the difference between what do you mean by continuous flow sheet and what do you mean by batch flow sheet, and what is the difference. So mainly the continuous flow sheet is going to be used to model steady state process, means my feed to the tower is continuous, product withdrawn is also continuous. Okay, but this continuous process system or say continuous flow sheet model can also model sub flow sheet or say hierarchy block. Okay, in Aspen Plus you have a word of hierarchy which represents the sub flow sheet, while in Aspen HYSYS it's a pure sub flow sheet word. So depending on your need or say depending on the software which you are using, you can use that particular option, and you can model the batch option in that one inside your continuous flow sheet. While in batch flow sheet, it is a totally depends a batch flow sheet where only the batch operation is going to be modeled. Okay, and in version 14, okay, now we have two types of batch subflow sheet, like batch process block, which is a new one, and this is a redesigned batch sub block. Okay, so this you will be able to see only in V14. If you have a prior version, you will not be able to see it. Now, before we start with our exercise part, we have 3 slides only. So we will cover this 3 slides first, and then we will jump to the exercise part. Okay, so now Let me even show you. Yeah, this model I already ready. We are going to model same things. When I say the continuous versus batch, so if you see currently the selection is continuous, and here in the model palette, if you see batch model shows both batch process and batch sep. Okay, batch process and batch sep. While if I'll change this to batch, if you see it gives me a warning that incompatible block for batch process type. That means the unit operation which I have selected is not capable to have this kind of batch separation block in the batch flow sheet. Okay, this refers to the continuous flow sheet and batch flow sheet, while this refers to the module which are there in each type. Okay, so I will show you how the batch flow sheet looks like later when we will do the exercise. Okay, so this both blocks which I have showed you, batch process and batch sep, are accessible from the model palette batch model tab, but it is available only in continuous flowsheet type only. The batch process refers to the batch reactor and crystallizer kind of modeling, while the batch sep represents batch distillation. So this batch reactor means it models the batch operation which may include reaction and or crystallization. Okay, so if this kind of things you want to model, then you should use this block batch process. But if you want to model a distillation system, then you should use batch sep block. This batch process is fully configurable. Subflow sheet can be built as per typical Aspen Plus flow sheeting practice. And this is a pre-packed subflow sheet, customized configuration from within the form. That means both are having some predefined information. Okay, you need to add the parameters as per your requirement. Okay, now we will learn how to create a new batch flow sheet. Okay, just since our intention is to learn the batch distillation modeling in the uh, webinar, but we are touching up continuous flow sheet and batch flow sheet, we thought to be included here. So now we are going to learn how to create a new batch flow sheet. So I will show you in the Aspen Plus itself. So if we go into the Aspen, this is my new blank file. Okay, I have not yet opened. When you open the simulation, this is how the window will look like. So if you see here under new, you have an option of new simulation or new batch process. So this new simulation refers to continuous flow sheet. Okay, and this new batch process refers to batch flow sheet. And here if you see, you have couple of templates: chemicals, gas processing, mining and minerals, refinery, specialty chemical, pharmaceutical, and so on. Okay, guys, just give me a minute. Yeah, so when you are clicking on this new, okay, if your intention is to model directly the batch flow sheet, you need to click on this new batch process and not new simulation. Okay, then the file will open in batch flow sheet. So I will show you, let's say batch process, you can select anything depending on requirement, chemical or specialty chemical. Okay, and let's say specialty chemical with English unit. I will say open. It will try to open the file in batch flow sheet. Now I will show you how you will be able to understand. Let's say if somebody has directly, I will add just one component, let's say benzene. Okay, and then I will select method. Okay, fine, NRTL it is selected. Okay, I'll go to simulation and I will show you how you will be able to understand whether this is a batch model or sorry batch method or batch kind of flow sheet or not. So if you see here, by default it opens the file in continuous. So what you have to do is you have to click on batch. When you click on batch, here the light, I would say the tortoise kind of color line or say border is appearing. This represents that the file is now currently in batch flow sheet. Okay, this flow sheet is in batch. Let's say if I'll show you this screen, somebody will directly recognize looking into this color that this is a batch process flow sheet. Okay, if you put your cursor here, it will tell you. But if you are not putting, but simply by seeing the color, you will be able to understand that this is a batch process flow sheet. And if you see under the batch model, you just have the option of batch operation. While if I'll go back to batch here and change into continuous, if you see that color has gone, that border has gone, and now batch model comprises of batch process and batch sap. Okay, it comprises of batch process and batch sap. So our intention is to model the distillation column, batch distillation column. We are going to model the things in a continuous process flow sheet only, because in batch process, I don't have that module available itself, correct? Without the module, I cannot generate. Here I can do the rigorous modeling of reactor only. Okay, so if somebody wants to do the batch reactor modeling, then yes, you can use this batch flow sheet option and do it. Otherwise, if the intention is to model the batch distillation column, though it's a batch distillation, but still you can do the modeling in continuous, because we are going to follow those steps that, okay, I'm going to first charge the material, then I'm saying that now start the distillation activity and so on. So we are going to put those sequential steps as well. Okay, so even though my flow sheet is continuous, the operation is going to happen in batch only. Any question on how you can identify or say open the batch file, batch process flow sheet? Anybody, any question, guys? Okay, now when we say batch flow sheet, okay, it contains couple of module only. Under model palette tab, you will be able to see this one: mixer, splitter, separator, exchanger, blah blah blah. Okay, and under each one you will be able to see certain block, like let's say for exchanger you will be able to see heater and heat X. Okay, let's say if this is my batch file, under exchanger you are able to see heater and heat X, versus if I'll change this to continuous, you will be able to see heater, heat X, M heat X, and HX plus. This M heat X represents LNG exchanger, or say multiple into the heat exchanger and multiple out from the same heat exchanger, like braze aluminum heat exchanger, which are typically used in cryogenic industries. Okay, so in batch flow sheet, we don't have a many more unit operations to be modeled. So that's why we are trying to list it here, like we are trying to highlight there. If your intention is to prepare a simulation in a completely batch process flow sheet only, then you should understand that these are the only available blocks through which you can do the modeling. And if any of the unit operation which you want to model is not available here, then you cannot use complete batch process flow sheet. Rather, you have to use the uh, continuous process flow sheet and try to integrate that with batch process flow sheet using the sub flow sheet or say hierarchy option. Okay, guys, so before I'll start with this exercise, anybody has any question, feel free to ask. Otherwise, I'll move to this exercise part. Any doubt, guys, before I'll start with the exercise part?
हेलो
Yes, yes, go ahead.
सर एक डाउट था कि सर हम सपोज हम सिंपल डिस्टिलेशन हम लेबोरेटरी बेसिस पे कैसा यूज करते हैं हम कि कोई भी कोई कंपोनेंट है डाल दिया, बाद में हीटिंग चालू कर दिया, और जो अनरिएक्टेड रहेगा वो और जो पानी निकलेगा कंडेंसेशन रिएक्शन रहेगा तो पानी निकल जाएगा, तो वो सेम रिएक्शन हम इसमें एस्पेन में कर सकते हैं सर?
Batch distillation does same concept. It works on the same concept. See, let me show you the image which we took is the same things. Okay, in laboratory the similar setup is there, correct?
Yes sir.
So batch distillation in Aspen Plus does same things. that you are charging the material, and then in laboratory what you are doing, once the material is charged, you are heating it up from the bottom, let's say, and then material gets evaporated. And what we are doing is we are trying to judge the distillation range typically for the sample, correct? Like
Yes.
let's say if I am adding 100 ml of quantity here and I am heating it up, I am saying that when 95% is remaining. So when the 5% material is evaporated and collected here from the condenser to the, let's say, reflux drum, I am trying to measure the temperature. What was the temperature? Then again my heating is continue. When I have 90% remaining, or in other words I would say 10% distillation is already happened, I'll report the temperature. So same things is done here, but here we are not interested in that distillation range, rather we are interested in our product composition.
Yes.
Okay,
और
so
सर हमें, और सर हम स्टार्टिंग में तो हम कोई भी सपोज स्टार्टिंग में तो हम सब मटेरियल नहीं डालते, सपोज 2 मटेरियल डाला, बाद में मिक्सिंग किया, बाद में वापस 2 मटेरियल डालते, वो भी हम कंपोजिशन एस्पेन में ऐड कर सकते हैं टाइम बाय टाइम।
सी आप जो बोल रहे हैं कि पहले 2 मटेरियल डाला, उसके बाद मैंने दूसरा 2 डाला, बट देन आर यू सेइंग दैट पहले मैंने 100 ml के मिक्सचर में 2 कंपोनेंट डाला, अभी वो पूरा कंप्लीट नहीं हुआ और बाद में वापस मैंने और मटेरियल डाला? इफ दैट काइंड ऑफ थिंग्स यू आर डूइंग, दैट मीन्स you are playing with your feed composition, which will have an impact on your product, correct? So you will not get the desired product purity. कैसे मिलेगा आपको प्रोडक्ट प्योरिटी? आपका फीड का कंपोजिशन चेंज होता रहेगा बार बार, तो आपका प्रोडक्ट प्योरिटी के लिए जो आपको ऑपरेटिंग कंडीशन चाहिए वो भी वेरी होगा ना. How you will be able to know that at a given temperature you will get a desired product purity if your feed is fixed, correct? And this is the reason we are saying that for high precision product purity we need to go ahead with batch distillation. Otherwise, if I'll go with continuous, जो आपने एग्जांपल दिया वो कंटिन्यूस जैसा हो गया कि आपका फीड जो था आफ्टर सर्टेन टाइम आपने और 2 कंपोनेंट ऐड किए, लेवल
नहीं
डिप्लीट
सर,
हो गया तो.
सर्टेन टाइम नहीं सर, थोड़ा मिक्स होने के बाद.
हाँ, तो मिक्स होने के बाद मतलब आपने डिस्टिलेशन चालू नहीं किया है, दैट इज व्हाट यू आर सेइंग. हीटिंग चालू नहीं किया है.
नहीं, स्टार्टिंग सपोज हीटिंग चालू नहीं किया है, स्टार्टिंग में मैंने 2 कंपोनेंट डाला, बाद में थोड़ा मिक्स होने दिया, मिक्स होने के बाद दूसरा 2 कंपोनेंट डालता हूँ मैं.
that can be model. see वो प्रैक्टिकली आप कर रहे हो बिकॉज यू आर ट्राइंग टू एंश्योर दैट कि कंपोनेंट ए एंड बी को पहले मैं डालूंगा तो प्रॉपर मिक्स होगा, उसके बाद कंपोनेंट सी और डी को डालूंगा तो फर्दर मिक्सिंग होगा. एस्पेन को वो नहीं समझेगा. एस्पेन को कैसा है, सॉफ्टवेयर को वो प्रैक्टिकली आप करें. सॉफ्टवेयर सेज in component list you are going to define 4 component and then you are going to add the composition of each component. जैसे आपने 2 कंपोनेंट डाल के मिक्सर बनाया और 2 डाला मिक्सर बनाया, और जो नेट मिक्सर आपका बना उसमें क्या कंपोजिशन है वो चारों का ए बी सी डी का, वो आपको एस्पेन में डिफाइन करना है. एंड देन एस्पेन अज्यूम दैट कि जैसे फीड मिलेगा वो कंप्लीट मिक्स्ड कंडीशन में है ये कॉन्सेंट्रेशन से, जो आप मैन्युअली हीटिंग चालू करने से पहले करते हो.
ओके.
So yes, it can be modeled provided you have not apply heat to the system. क्योंकि सॉफ्टवेयर को नहीं समझेगा ना, उसको आप 2 कंपोनेंट दो या 4 कंपोनेंट दो, उसको आप जितने कंपोनेंट देंगे और सबका आप मोल फ्रैक्शन या मास फ्रैक्शन या वॉल्यूमेट्रिक फ्रैक्शन आप डिफाइन करेंगे, उसके हिसाब से आपके फीड रेट के हिसाब से वो रेशियो अंदर डाल देगा. कि लेट से आपने 100 डिफाइन किया और आपने 33 बोला तीनों का मोल फ्रैक्शन, तो 33 kg ऑफ ए, 33 kg ऑफ बी एंड 33 kg ऑफ सी करके वो बना देगा.
ओके सर.
Okay.
Okay.
Yeah, thanks.
Thank you, sir.
Okay. Anybody has any question or should we jump to the exercise part because we are having just 40 minutes now? Okay, let me start with the exercise so that whatever we have learned, you have a better clarity on that part. So now in our example, what we are going to do is we are going to model a batch distillation column. Okay, but here what we are going to do, what we are going to do is we are going to add 1 kilomole per hour of benzene and a toluene with 0.5 kilomole per hour with molar flow rate. Each is going to be distilled in batch column which consists of 6 equilibrium state. This is my problem statement. Okay, in the column with the partial condenser and feed is fed on the 6th stage in the column and it is charged with equal mole fraction of benzene, toluene and nitrogen with 1 kilomole per hour, 25 degrees C temperature and 1 atmospheric pressure. That means I am trying to replicate existing batch distillation column which is there in the plant, and I am trying to mimic same things in the Aspen Plus. The condenser reflux drum hold up and pressure is calculated from tray or packing which is present in the column. So we are not defining the pressure. We are saying that based on the tray or packing which we have selected or say there in the column, please calculate. Initially, we are assuming that the column or say pot is empty, but it contains inert gas. Okay, some amount of nitrogen is already there into the tower because my atmosphere should be air free. Correct, O2 free. It should be inert. The column has two distillate receiver for liquid and vapor. So that means if my condensate or say condenser is not a total condenser, means it's a partial condenser, because in the problem statement if you see we have mentioned partial condenser. So that means it has vapor and liquid both at the outlet of condenser material stream. So reflux drum contains both vapor liquid. So I am saying that vapor is going to a separate distillate and liquid is going to separate distillate, sorry, separate receiver. The condenser has a 20 square meter of heat transfer area with coolant mass flow of 0.01 kg per hour. That means we are fixing the condenser geometry that it has 20 square meter or say 20 meter square of surface area available, and the coolant flow rate, maybe cooling water or any other utility, is 0.01 kg per hour. Port is vertical, charge vessel is a vertical vessel with a flat head in the top and bottom. That means we are talking about a cylinder. Okay, it doesn't have any kind of top and bottom descent like ellipsoidal kind. And the dimension is 2 meter 10 to 10 length and 3 meter diameter. Okay, the jacketed heating is provided to the pot which covers the bottom as well. That means here instead of having a reboiler concept, we are saying that a pot with a jacket heating. So this jacket heating medium is maintaining a 25 degrees C with 0.5 kilowatt per square meter Kelvin overall heat transfer coefficient. So it plays a role of reboiler. Okay, this heating is transferred to the content inside it and it will play functionality of reboiler only. Column has a tray with a spacing of let's say 0.5 meter and a 3 meter diameter. So these are all the information which I have. Now we want to model this batch distillation. So the step what we are saying 100 kilomole per hour of feed is going to fed to the pot for 1 hour. That means we are saying that we want to feed the material to the pot for 1 hour to ensure that my pot is completely filled. Then the step 2 which we are going to do is we are saying that stop feed to the pot and then start heating for 24 hours. Okay, so as we discussed in the subsequent previous slide, that in the batch distillation we are doing the things in a stepwise. We are charging the feed and then we are starting the distillation operation, that means heating. Okay, and what we are saying that we are going to charge the material for 1 hour. So more or less my pot is going to filled. If you feel that your pot is having a bigger dimension and you need more material, okay, if the pot volume is more than this quantity, then you can feed it for a higher duration. Ensure that your pot is completely liquid filled, let's say. Second step is once the liquid is filled, you can stop the charging to the pot. Next step which we need to do is start the heating of the unit. And we are saying that we will heat it up to 24 hours. And we are saying that the third step is, let's say somebody is saying that why this 24 hours? Why not 10 or 20 or 15? How you will know that you need to heat it up to 24 hours only, or maybe sometimes you need more than that as well, correct? So for that, we are supplying the extra step stating that terminate when the liquid mole fraction of benzene in the reboiler remained 0.1. Okay, so that means what we are saying that we are supplying the heat for 24 hours, but we are stating this additional step as well that I want to terminate my heating to the system when the liquid mole fraction of benzene in the reboiler remains as zero point 0.1. That means when the concentration of benzene in reboiler, or say in the bottom section of my distillation column, is 0.1%, stop the heating even though it has not achieved 24 hours. Let's say within 1 hour your concentration, your system is reading that concentration of benzene is zero point 0.1. Simulation is going to stop and it will show you that okay, your batch time for this much of concentration is 1 hour. Within an hour time your batch is going to be complete in terms of distillation, and 1 hour time is for the feeding. So within 2 hours your one batch is going to be over. So that batch time is also going to be calculated using this tool. So any question on this problem statement? If yes, go ahead. Else I will start modeling the batch distillation thing in the Aspen Plus.
So
Okay. Yes, go ahead, Harry.
this information are like minimum information required to run a simulation for a batch.
So you are saying that like how much minimum information you need to run the simulation, correct? Harry, can you unmute and say?
Yes,
Okay, okay.
yes, that's
So
what for me.
yes, so if let's say we are trying to do the modeling, yes, existing system modeling, these are the information you need. And let's say if you are doing the new system modeling, then you need to put some assumptions, correct? Like during the design stage, you don't have the column diameter known. So you will do some assumption and you will try to see that at which dimension you will be able to get the desired separation. So yes, these are the minimum information you need, because without geometry, it is not a worth idea to model, correct? Without dimension, how you will ensure that the fixed quantity is going to feed? You have to provide the dimension, correct? Otherwise, how it will understand that this much quantity is there and this is the concentration I need, or I would say after so and so time I have to stop. So dimension is required. These are the information you need to put. Yes, this is the minimum information we need to provide.
Okay, sir.
Okay, because see, if you are saying that, let's say jacketed heating medium is maintained at so and so temperature, but then either you do an actual reboiler modeling with the utility details in it so that it will understand that this is the heat transfer coefficient it is going to offer. If this is not available, you can simply say that jacketing system having so and so temperature, or it is maintaining so and so temperature with this is the heat transfer coefficient. So it's up to us that how we want to model. Since our intention is to see our product purity, okay, and we want to fix the dimension of column, we are trying to put directly the heat transfer coefficient. Later, when the further detailing is done, that time you can ensure that when the reboiler design is done, it has to ensure that it should offer this much of heat transfer coefficient. Then and then your reboiler is going to work. Or say your column is, I would not say reboiler is going to work, but you will not get the desired product purity if your heat transfer coefficient is less than this. Okay?
Yes, sir.
Yeah.
Hello, sir.
Yes, yes, go ahead.
Sir, sir, my question is, let's you mention in the that can you show me that problem statement on the slide?
Yes.
So there you are mentioned our feed is fed at 6 stage of the column. So I'm just confused if we are charging the pot directly or we are feeding in the like continuous in the column like that. Because if we consider the batch, then we should charge it directly into the pot and then we'll start the heating, that kind
Correct,
of
correct,
thing. Though.
correct, correct. So once we will do the simulation, this doubt will get clarified. Okay.
Oh, okay.
Okay. Now let me start so that things would be pretty clear to you. Otherwise, we yes, yes.
Sir,
Yes, Sangeeta, go ahead.
sir, we can Sir, can we change the parameters after doing the design? Like, if we are not getting the like desired purity, we might be increasing the dia stages. Can we do it in this
Yes, yes,
operation?
you
Like
can.
after designing,
Yes, you can
we can change
do
the
it.
parameters.
Yes, you can do it. Na? Why not? See, modeling concept is still same as your continuous. Only thing is here the operation or say solver is running the system in a batch wise. Like for 1 hour, the feed is fed to the system. After that, it starts the heating and then it will terminate when the concentration of the benzene is reaches to 0.1. Otherwise, yes, it's not that once you did the modeling, you cannot change the parameter. No, you can.
Sir,
Otherwise,
one
how
more thing.
you? Yes, go ahead.
Sir, why is nitrogen considered as a in the mole fraction?
See, when the see, whenever we are starting the unit, okay, we should have the atmosphere in the vessel as inert. It should be air free or say oxygen free. Correct?
Yes.
But for that, you should have to use inert gas. Now, the easiest available inert gas is nitrogen.
Yeah.
So people normally do inerting of any equipment in the plant using nitrogen. Now, when you do this inertization, have you seen that nitrogen inertization is done in the plant and then nitrogen is removed from the system before you introduce hydrocarbon in it? No, correct?
Yeah, it is not.
Yeah. So when you are charging the material, the nitrogen which is there in the system is there. So you have to consider its concentration, correct? Otherwise, your feed, see, you are adding only benzene and toluene in the feed, in the charged vessel, but nitrogen is there. So definitely it is in vapor phase. So when you are adding the liquid, your nitrogen is going to get compressed. But at the same time, you have to understand that the nitrogen is there. So your mixture concentration is not only toluene and benzene, but it also has nitrogen. Have to have a true representation.
Okay.
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 So now without spending much time on the discussion, let me begin with the modeling so that you will get a better clarity. And then if you have a question, you can ask, not an issue. Okay. So we are going to create a new simulation. And as per our problem statement, we are going to add these three component: benzene, toluene, and nitrogen. Okay, so if I'll go back to my property environment and under component, we have already added benzene just for the earlier check. Now I am adding toluene. We'll say yes, and then I am adding nitrogen. Okay, so I have added all three component. Now for the next part, okay, what is the next input? Either you directly jump here where the red half fill circle. Okay, and if it's not clear, it is better that you just click on this n arrow, means next input. It will tell you what is the next input. It will directly navigate there. So if you see here, since we added a new component, it has already added and upgraded the parameter. But as per our problem statement, we need to select srk as a property method. Okay, not nrtl. So we are going to change it to rksolve. Okay, and now I'm going to click on N. It will calculate those binary parameters or say temperature dependent binary parameters for this benzene, nitrogen, benzene, toluene again. So with this, if you see required property input complete, that means my job on the property environment is done. Now I can switch to simulation environment. Okay, so now we are here into the simulation environment. Now we know that we want to model, let's say, batch distillation unit. Okay, sorry, before that we need to add these two property sets. Okay, so let's say if somebody wants to monitor the couple of parameter for a mixture, then you need to add the property set for viscosity and say thermal conductivity of mixture. So for that you have to go to this property set. Okay, if you see here, we have couple of, okay, we have couple of, but if these are not fulfilling my requirement, I will say click on add. I will add a new one. Okay, it's PS1. Okay, if you see here, this is red one. Now here what I will do, I will click on this search. My interest is to add viscosity, but I want a viscosity of mixture. If you see, this is a kinematic viscosity, this is viscosity of pure component, and this is viscosity of mixture. So we are interested in viscosity of mixture. So I need to select this. Okay, I need to select this. Okay, and then I will say okay. It will be added here. Now here you have to understand that this mu mx represents viscosity, and viscosity unit is, let's say, centipoise. And the second thing which we want to add is thermal conductivity. So I'll again go here and try to search, let's say, thermal, and this is the thermal conductivity mixture kmx, and for pure component it's only k. So our interest is to model thermal interest is to generate the property for mixture. So we are saying that thermal conductivity mixture, and its unit is, let's say, BTU per inch or square feet degree Rankine. Okay, it depends which unit you have. Accordingly, you can change it. Okay, I am just selecting particular one. And then in the qualifier, you need to select the phase of the fluid. We are saying that the phase of the fluid is liquid. With that, if you see, your property set is now turned into blue. That means this property set is now completely defined. Okay, so now we can go to the flowsheet model part. Okay, so if you have a specific property which you want to generate, then you have to define those likewise. If you see, my existing file contains many more things, but just for your knowledge, I have showed you how you can generate a property set, and then you can even rename this like mixture, viscosity, thermal conductivity. Okay, see, try to understand here, there is a limitation that you cannot have more than 8 alphabet. Okay, whenever you want to write anything in the Aspen plus, okay, even in material stream or say your distillation column or maybe any unit operation, the nomenclature should not have more than 8 alphanumerical text in it. So that's why here if I want to add the, it will not allow me to add the. If you see mixture, viscosity, thermal conductivity, so you should know that this represents what. Okay, so based on your convenience, you can rename this property set. Now we will start with our modeling part. So our interest is to model batch separation or say distillation column. So I'm going to select this one. I am adding it here. It will be added. Now here, if you see, we want to model this setup. That means we are going to charge through this, and we are also introducing feed here. Okay, so we have created this batch sep block, and now we are going to add this 4 stream. Okay, feed stream, charge stream, R1 and bottom. Okay, so I am adding 4 material stream. I'm saying feed is entered feed is entered here. Another charge stream is here. This is my, let's say, product stream, and this is my bottom stream. Okay, we have added 4 stream. I am renaming is that this is my feed, this is the charge.
Sir, feed will be feeded to the will be charging to the bottom only, right, sir?
Wait, we will discuss all those things. Okay, all your doubts will get clarified. Sorry, let me pull it here. This is, let's say, bottom. Now here, try to understand. Okay, as we will define these things now, you will get a better clarity. Okay, that what we are considering in charge stream and what we are considering in feed stream. Okay, if you see here, we did this part. Okay, we placed the unit operation and we connected stream. Now try to see in the charge stream what we are saying, that we are charging. Okay, we are fixing the temperature of the stream, pressure, flow rate, and the composition as blah blah blah. Okay, so let me first put that. Once we will do this two stream modeling, your doubt will get clarified. Okay, so I'm saying that temperature is 25 degrees C. So let me change the unit set to SI. SI do not have it. Okay, metric bar. Yeah, so 25 degrees C. Then pressure is 1 atmosphere. So I need to change it to ATM. Then we are saying that the flow rate is 1 kg mole per hour. Okay, so I'm changing the basis from mass to mole, and value is 1 kg mole per hour, and the composition available is in mass basis. See, try to understand. The flow rate was available in mole basis, but composition available is in mass basis. So I am going to change here this mass flow to mass concentration, sorry, mass fraction. And then I am defining the value as 0.333, 0.333, and 0.3334 to have it as 1. So with this, my charge stream is defined. Now let's define the feed stream as well. Okay, so that you will get a better clarity. Now in feed stream, what we are saying that temperature, pressure, and flow rate is same. Okay. Now temperature is 25 degrees C, pressure is 1 atm, flow rate is on a mole basis. Okay, and value is 1. But what we are saying that the fraction, the bifurcation of this 1 kg mole per hour is zero point 0.5 for benzene and toluene. That means here I am saying that I have the ready-made flow rate. I am saying that benzene is 0.5 and toluene is 0.5. Now I'll explain the difference why we have these two. Initially, when we are charging the material, yes, it is being charged into the tower, sorry, the pot. And when the system had the nitrogen in it, okay, we are saying that this nitrogen concentration is also accounted here, correct? Because we have added a material 1 kg mole per hour, which has zero point 0.3, zero point 0.3 nitrogen, benzene, and toluene, correct? And now we are saying that this feed is charged. Okay, so this feed we are saying charge to the sixth stage, and my sixth stage is refers to the bottom stage only. Okay, so if I'll go to my flow sheet, sorry, my PPT, and I'll show you the original laboratory level scale. If you see, we are charging here, so it is as good as like I'm charging on the last stage, correct? So what we are saying that many times you have seen that you have multiple feed to the system. Instead of one feed entry, you have two feed entry as well, correct? So maximum things we are trying to feed it from here. But if you have two entry, you can even add the material from top as well. So what will happen here? The feed is entered from the sixth stage, it will collected here, and you are charging the vessel as well. So with this two material, your vessel is going to filled. Clear? The feed is not going to top, it is going to come back here only. So I think Sangeeta has asked this question, if I'm not wrong, correct?
Yes, sir. Yes, sir.
So now clear why we are adding two stream and what is the functionality of this two stream.
Yes, sir. I
Ultimate,
have.
ultimately it will come to the vessel only. So here, if the flow rate of this stream is low, let's say my source is having 1 kg mole per hour, and if the vessel volume is more and you need 2 hour time, so what you can do is you can introduce another nozzle, either you introduce here or you introduce here, it is same. If the pipe is limited, let's say pipe is limited, you cannot push the material more than 1 kg mole per hour, then you have to either increase the pipe size, or you can add another nozzle or say another pipe through which further 1 kg mole per hour of material is going to be introduced. So it's up to us. During design stage, you have a handle. Okay, so someone will say that I will have a single pipe, okay, with bigger diameter, and I will fill the vessel. Someone will say that if I have two pipe and within the same flow rate, okay, 1 kg mole here and 1 kg mole here, I am able to fill it the tank in 1 hour only. So it's okay that if by adding here, if you are gaining something, some more benefit, then you can keep it here. Okay, so during design, you will check that, okay, with this 2 feet, what kind of batch time you are getting, versus if you are adding 1 feet, sorry, one feed nozzle, only the charge stream, what kind of benefit. So during design stage, you have to study these options. But the purpose is that it has to fill the material only into this charge vessel and this system. Okay, so it is trying to fill the system. Now we are going to follow the next step.
Sir,
Yes.
Sir, this is before the starting the distillation. No? During distillation, we are not going to use this. I'm just practically I'm trying to understand. During
Yes, yes.
distillation feed, yeah.
This is like the first step when we are charging the system. Once the step one is over, my charging is over, it is going to stop the feed, and you will see that now the evaporation has started and vapor generation has been happened. So this thing I will show you live as well. Okay, so just let me finish
Okay.
the whole modeling so that you
Okay.
will
Okay, sir.
understand
Okay.
how
Yeah.
this
Okay.
Aspen is doing. Okay, whatever you are thinking, practical things, or maybe you have seen in the laboratory or plant, same things you will be able to see here. But for that, I have to complete the whole modeling part, correct? Okay,
Okay, sir.
so our next step is now we are going to open the batch sep unit and we are going to configure the system. Okay, so I am going to double click here. And now we are saying that by default, if you see here, it takes number of stages 10. But if we are modeling the existing system, you can do the number of stage input as per the exact details from the GA drawing, let's say 6. Don't see here, the feed was earlier like let's say when it was on 10, you were able to see feed here. Don't see right now here the things. Okay, once our modeling part is done, we will refer to this drawing. I'm saying my feed is at, sorry, my column has total number of stages 6. Okay, and then we are saying that we have two receivers. Okay, we have two receivers. So number of receiver we are increasing to 1 to 2. One is for liquid and one is for vapor. And for that, if you see, currently the condenser type was by default selected as total. That means it is only having a liquid phase here, complete liquid. So part goes to reflux, remaining goes to liquid receiver only. And that is the reason this receiver is empty. But as soon as I'll change this to partial, as in our problem statement, we had a partial condenser, correct? We had a partial condenser. So that is the reason we have changed the condenser as partial. Okay. Okay, if you see, set the condenser type as partial and check the reflux drum present checkbox. That means we are saying that reflux drum is also present. So if you see, reflux drum has added, and now you will see here liquid comes here, non-condensable or say vapor directly goes to your outlet line, and you have liquid line. Still wait. Okay, still wait. Still you haven't connected the second. So we still need to complete the modeling part. Okay, now we are saying that for the pot heat transfer, we are going to use rigorous method. So that means the jacket, okay, jacket through which we are supplying the heat to heat the material, we are saying that the let model to perform the rigorous calculation. Okay, so these are the things which we need to consider. And we know that, okay, we know that our initial condition was empty as per problem statement, correct? In the problem statement, we mentioned that, where it was, yeah, initially the column is empty, correct? So that is the reason we change our initial condition, which was earlier on a total reflux. As a by default, we have changed it to empty. Okay, so these are the initial input we need to do in the configuration tab. Okay, configuration tab. Now, if you see, this has not turned into green, that sorry, blue. That means some more input I have to offer. So when you click on this next, it says pressure hold up is specified is not allowed unless initial condition is total reflux. So that means this pressure and hold up is selected as specified as a radio button. That means we are specifying the pressure. So if we want to specify the pressure, then initial condition should not be empty, it should be total reflux. So if my initial condition is empty, that means I have to have this pressure and hold up as calculated from tray and packing hydraulics, which was there in our problem statement as well, correct? Somewhere it was there, yeah. And pressure is calculated from tray or packing present in the column. So see, since you guys are not knowing things, we have highlighted each and everything in the problem statement. But if this is not there, and if you have selected this as empty, the way I showed you, okay, when you click on next, it will give you a warning that this is not allowed unless initial condition is total reflux. So if I will make this as total reflux, configuration part is done, but my requirement is empty. So I have to change it to calculated from tray or tracking, and then it is done. Now I have to go to stream part. Okay, the second tab is stream. So now we are going to put the information on that. Specify the stream tab means set charge stream as the pot charge and the basis is flow rate basis. So we are saying that the charge stream, the flow rate basis is mole. Okay, the pot charge is charge stream, whether the feed stream you want to charge into the pot or whether you want charge stream. Okay, so we are saying that here we have only a single stream connected to this pot, it will have only single. But if this feed I have connected here as another, then I have an option to select either feed or charge for the charging, pot charging. Okay, now additional stream which we are saying that feed stream, we are feeding on the sixth stage. Okay, so we are charging this on sixth stage. Okay,
So you are muted.
now I'm able to hear. Like, am I able to hear you?
Yes.
Okay, okay. I don't know why today this is happening. This is even surprising to me as well, like automatically muting is happening. So if you see here, okay, sorry, this is already my converse file I'm showing you. This kind of representation you will be able to see. And if you see here, the connection is connected to 2. Okay, so here in the stream, okay, we have added all those things same in our other simulation file. My charge stream is connected to the pot, basis is mole, feed is connected on stage number 6 on the stage and basis is mole. We have two receiver, product is R1 and no side drop. Okay, now we are going to specify pressure and hold up tab. Now if you see here, already we have selected this one. Okay, so it is done. Now the next tab is condenser tab, where we are going to define the heat transfer area of the condenser and the coolant flow rate. So in the condenser, if you see, it has by default some parameter. Okay, but our requirement is a specific. We are saying that we want a coolant flow rate as 0.01 kg per hour. So I am saying that flow rate is 0.01 kg per hour and surface area is, or say heat transfer area is 20 square meter. So this we are defining. Inlet temperature, if you have a known temperature from the field, it is different from this, you can change it. Okay, not an issue. This is your utility temperature. Just for our conversions, we are not playing it with it. You change it from 10 to 20 or maybe actual value, not an issue. Okay, so we have defined the condenser tab as well. Now we are going to define pot, the dimension of pot, correct? So here we are going to define pot. We are saying that my pot is vertical, which was there in my original problem statement. And we mentioned that there is no head. It has flat head, means it is like a cylinder. So here you will be able to see the actual things. This is how your pot look like. But here it has head. So don't believe in this schematic. Okay, this is a general schematic for batch SAP operation. Okay, so if you want to see the actual details, you have to go to this pot tab. Then you will be able to see that do it have head or not. Okay, if I let's say make it as elliptical, okay, here you will be able to see head, that top is elliptical, bottom is flat. But in our problem statement we mentioned that both head is flat type. Okay, and then we are going to define diameter and 10 to 10 length. We mentioned that diameter was 3 meter, 10 to 10 length was 2 meter. Correct? 2 meter, 10 to 10 length, diameter was 3 meter. Now I think we haven't missed anything. Let me see. Yeah, this is done. Reflux is reflux ratio. Okay. Okay. Now, before we will go, let me just check here as well. Yeah, this is the same thing. Okay. What is also we have selected vertical,
Sir,
flat,
in the
flat.
convert file, it shows that the condenser outlet is also connected with the second vessel.
Yes, 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 yes. I will show you. I will show you. Not an issue. Okay. Wait. That will be there. Okay. I will show you the same things in our diagram, and then I will show you how this is working. Okay. So I'm just trying to see that before I'll move to the next step, whether anything I have missed or not. Okay. Now we are going to specify the batch SAP heat transfer information. So let me go here. So if you see here, this batch SAP is now done. Okay. B1 part setup is done. Okay. Setup is done. We were here into the setup. My setup part is done. Everything I have defined, everything is now blue. Now the next thing is heat transfer. Okay, whichever is red in color, that we need to fill. So now we are going to define this heat transfer part. So we are saying that, okay, we are saying that we are going to define this jacket heating. Okay, that the medium which we are going to use, sorry, the medium which we are going to use is having a temperature of 25 degree C, and the heat transfer coefficient we mentioned was 0.5 kilowatt square meter Kelvin. So heat transfer coefficient is 0.5 kilowatt meter square Kelvin. Correct? Yeah. And now with that, if you see, this has converted into blue, means the information which you have to define is done. Now, if you see here, we have another snap as well where we have the option of heat loss. So this feature is only available in version 14. Okay. So if you have a version lower than that, you want to be able to see this. And this refers to the ambient temperature loss. That means if the ambient temperature is lower than your heating media temperature, you will see that from heating jacket itself, you will lose some amount of heat to the atmosphere if it is non-insulated. Okay, if it is a bare jacket, then you are going to lose the heat duty. So in that case, you have to fill this information, but this is possible only in version 14. If you have a lower version, then this is not possible. So the one which I am currently using is V12. So I don't have that an option. Okay. Now the next thing, if you see here, is we need to define the initial condition. So we are going to define the initial condition. We have mentioned that initial condition was empty, but along with that, it has nitrogen in it. Okay, it has nitrogen in it. Okay, as a paired gas. So with that, my connection on initial condition, sorry, my definition on initial condition is done. Now I am going to define column internal. Okay, so for that, we are saying that it has only one section, stage 2 to 5, and tray type with spacing which we have mentioned was zero 0.5 in the problem statement, and diameter as 3. So I'm going to click add, and this internal one, I'm saying add one, start stage is 2, end stage is 5. It is tray type, tray spacing is 0.5 meter, and diameter is 3 meter. Okay, so with this my internal is also defined. Okay, next step is we need to define the operating step. Here we are going to define the sequential step that I want to charge the system and then I want to start the distillation. Okay, so first we are going to create charge operating step, means I'm clicking add new. I'm changing the name to, let's say, charge, and I will try to define this thing. Yeah, now here in the charge what we are saying, okay, what we are saying that we want a feed stream, molar flow rate as so and so, jacket medium temperature maintained as so and so, and condenser doesn't have any kind of things. Okay, so we are saying that the stream is feed, id is definitely charge or feed, that we need to fix, and what we want is mole flow rate. Mole flow rate is this, and the value we are saying as 100 kilomole per hour, 100 kilomole per hour. Now second thing we are saying that jacket heating. Okay, and we want to maintain temperature as 25 degree C. And the third thing we are saying that condenser, and at the beginning we are saying that coolant flow rate would be 0. So in my first step we are saying that when we are charging the system, okay, I want to charge using this feed stream. Okay, now you see here both charge and feed has come down here. Okay, so earlier it was here, but I am saying that I want to charge it here directly. So I mentioned that during this operating step, charge during charging step, feed it using the feed stream with this much of flow rate, 100 kg mole per hour flow rate. So in my normal material stream, I have defined both stream with 1 kg mole per hour. But I am saying that during charging, increase the flow rate of this stream to 100 kg mole per hour, maintain the jacket temperature as 25 degrees C, and there is no condenser coolant flow rate. Okay. So that means the liquid is filled, heating is this jacket heating is trying to maintain the temperature, and I am saying that duration would be 1 hour. Okay, so that means this charging is going to take place for 1 hour. Now the next step what we want to do is we want to create a distill operating step, the second step. Okay, so I'm going back to this operating step. I'm going to add a new, and I'm changing the name to distill. I'm clicking view, and I am adding the detail here that in the distill, I am saying my feed 0, jacket heating, increase the temperature to 200 degrees C, and condenser flow rate this much. Okay, so feed ID is, let's say, feed, mole flow rate is 0. So when the next step was there, it will cut the feed. Then jacket heating, we are saying that increase the temperature to 200 degrees C. Okay, that means heating has applied. And then condenser coolant flow rate, we are saying it to 30,000 kg per hour. So that means whatever vapor content is coming, it is trying to cool down using this flow rate. And now what here we want to do? Okay, first thing, somebody, if you see here by default it takes 24 hours. See here, duration stop if process variable trigger value not reach in 24 hours. That means if within 24 hours, if the target value is not achieved, it will stop. But we are saying that we want to run it for 24 hours, or we are saying that stop if the benzene concentration in the port is reaches to the point 1. Okay, so we are saying that location is my pot process variable, I am saying liquid mass fraction. Component is I'm saying benzene. Let me see. Yeah, mole fraction. Sorry, mole fraction was our statement. Okay, and then we are triggering that at 0.1 fraction, my system should get stopped. Okay, systems should get stopped. Now let me go back and check. Did we miss something so that we are not getting same reaction here? So let me check whether I missed something or not. We should get. Okay, don't worry. Number of stage 6. It's vapor liquid. It is partial reflux drum present 1. Yeah, if you see, we missed to change the vapor location, that we want vapor in the receiver too. So as soon as I will change this vapor location, that vapor I want to collect in condenser receiver number 2, vapor has connected here and liquid is now here. Now question clear, guys? I think somebody has asked that in the converge file we had a different representation and the file which we were building having a different. So now clear? Okay, so with this
Yes.
our input part is done. Now my model is ready to run. If you see here, now it says required input complete. Okay, and we are ready to run. So now you have to focus this part. When I will run the model, okay, when I hit this run button, you have to see this part. You will be see the dynamic behavior of how it behaves. Okay, so let me hit the run button. And if you see now here on the my pointer, it tries to fill the system, correct? Try to focus on my pointer. Okay, it looks like it is trying to fill, and then after some time, if you see here now, the color has changed. Okay, color has changed. If you see, it has now started. This is like pause. Material is started filling. It has filled now. And then if you see now, level has depleted, and here you are able to see the liquid transfer. Correct? Now this has stopped. Okay, if you see here the step also, it was showing current operating step is distill. Now it has completely stopped. The material is now no longer coming here. When it was coming, you are able to see the dotted line. Okay, so this is how the model is calculating. And now if you see, it says result available. So if I'll go here and if I'll do the right click and see the result, I'll be able to see that how much time it took to converge the completion of my system. So if you see, charging took this much, distill took this much. Okay, then pot, distill receiver, and so on. So this is how you can see the result. Okay, you can see the result. Okay, this is how it is going to work. I will again show it if you want how these things can be interpreted. Let me reset and then run it again so that you will be able to see that how it is running. And try to see here the operating state, like operating step, it will show you the charge and distill both. Okay, so let me hit the run button and try to focus here as well. It has not yet. Yeah, if you see current operating step charge, so it is trying to charge the vessel. Then it has shifted to operating step distill. So now the distillation is happening. Initially the vapor is coming, now liquid is coming. It is depleting until it will achieve the step. Here you will get the material. Now once the material stop here, if you see, it has emptied out and then material has stopped. That means operating step is still distilled, and after certain time this will go away as well. And you will be able to see here that result available. So this is how you will be able to calculate your batch system modeling. Any question, guys, on this modeling part? And I hope now you got a pretty good clarity on this batch distillation modeling.
Can we change the time, that time duration you have put as a 24? Then that can we change?
That is a default limit of 24 hours. Okay.
So if I would like to like my batch should be in 6 hours to be distilled out.
Yeah. So what we are specifying here that let me I think it takes time. If you see here, what we are saying that process variable stop if the variable trigger value not reach in 24 hours or if it reaches this. So if it reaches before that, like if your batch is completing in 6 hours, that means if you are able to achieve this fraction value in 6 hours, you will be getting the time as 6 hours only. Your batch is going to stop in 6 hours. This
So
is the limit.
what will be the effect then?
Means the runtime
Means
here on the result, you will be able to see the different value. Here in the result, the batch time which you will be able to see here. Okay, the time from start of batch, time from start of first batch. Okay, the batch time, how much time it took, like this one is going to be different.
No, it's our input. Then what should be the impact if I put 6 hours?
Let me show
We
you.
might be sir, we might be like we might be getting the desired purity of the component in 7 hours, 7 hours, 8 hours also. We can't keep like 6 hours because
Yeah,
we can't
let
decide.
me explain. Let me
We can't
explain. Let me
decide the
explain.
purity of the.
Correct, guys. Let me show you. Okay, I have changed it to 6 hours. Okay, don't worry. You will not be able to get the desired product purity. Simple. If you fix it as 6 hours, if you need more time to complete that activity, then you will not get the product purity. Simple. Your product purity will not be the one which you are expecting. Okay.
Okay.
So let's see. This is still like in the operating step only. Yeah, now we have the result. So if I'll go here, if you see now it says 7 hours. So it has run only for 7 hours. And the fraction which you requested was not fulfilling probably. Okay. So you need to check each and everything in detail. And you will be able to see that within 7 hours really are you getting it, and that is the reason by default it took 24 hours, and if you are getting a desired product purity before that, you will be able to get the different value. Okay.
Okay.
Model will predict that how much time it need to converge it. Okay.
Okay.
Okay. Yeah,
Sir,
thanks.
is it like fixing the pot? Sir, is it like fixing the pot and giving the input? PD has the input, and in the output we will be getting the distillate.
Yeah, at the output you will get the desired product purity, whether the product purity is achieved or not. And second, you will also able to understand how much time you need to achieve that much of desired product purity, or I would say how much time you need to have that complete distillation. Okay, because as we saw in the simulation, in the distill step, slowly the level was depleting, correct? So after charging, how much time your system needs to complete the liquid material, okay, to empty out the vessel by means of recovering through the overhead section, and now the residual part is only remaining. So the next batch, or say next charging, when it is going to start, okay, let's say within 1 hour we are charging, and then you need 3 more hours to complete, or say to empty out that quantity with your desired product purity. That means the next material charge will start after 3 hours only. So first batch requires 4 hours. So each batch requires 4 hours. That means within a day you can have a maximum 6 batch. So you can calculate this kind of things. Okay.
Sir, I just want to clear about feed and charge, sir.
Hmm.
I just want to differentiate about that, sir.
Yeah.
I can
So
get that fully.
yeah, got it. So see, charge is my initial charging. Okay, initial charging when I am saying that it has nitrogen content in it. Correct. It has nitrogen content in it, because initially when I'm operating the vessel first time, it is nitrogen inert atmosphere. So when first batch is prepared, okay, it contains nitrogen as well. But when my condenser was a partial condenser, okay, condenser was a partial condenser, and when I am running this system, it also removes the vapor. So along with vapor, your nitrogen will also go out. Okay, and that is why in our charging step we haven't used charge stream, we have used feed stream. So in the next batch the environment is free from nitrogen. Okay, so that's why we use the feed stream for the charging and not charge stream. Charge stream is my first batch initial state composition. Okay, but I'm saying that I am feeding using feed stream only, not charge stream. Got it?
सर
Got it, sir. Got it, sir.
सर
Yeah.
नाइट्रोजन यूज नहीं कर रहे हैं तो एयर हम हमें देना पड़ेगा ना?
सी एयर आप दे सकते हैं प्रोवाइडेड द
Sir, your voice is not audible.
ओके फाइन. सो नाइट्रोजन जो मैं आप बोल रहे हैं कि नाइट्रोजन की जगह एयर देंगे. सी द रीजन व्हाई वी आर सेइंग नाइट्रोजन इज ऑलवेज प्रीफर्ड इज इट इज having a inert characteristics, it is not participating in any kind of reaction. If you have air, yes, it has 78% nitrogen but 21% oxygen, and if you have material which can easily react with
Sir,
oxygen
your
at a
voice
given
is
temp.
not audible.
Sangeeta, there is issue at your end. Okay, try to connect with the better bandwidth internet. So what I'm saying, if any component which is there in the vessel at a given temperature, if it can react with oxygen easily, it may lead to some disaster or maybe some issues. Correct? That is the reason we are saying that nitrogen should be there as an inert. You should not use air. Never in the plant air is used for inertization. Yes, it is used just to remove the hydrocarbon concentration and to hand over the equipment to the maintenance people, but not for taking the unit back into the operation. Okay.
Yes.
Okay, so I hope now you had enjoyed this session and you got a pretty good clarity on batch distillation column.
Yes, sir. Absolutely, yes, sir. Yes, sir.
Okay, good. So if no more question, let's conclude our today's session, and I hope you have learned a lot and try to incorporate this learning in your future project or maybe your ongoing project for the better gaining of the technical aspect. Thank you. Have a good rest of the day. Bye bye.
Okay. Thank you, sir.